Okay, so for the last several lessons we've been talking about scatter plots and regressions. And now what we're going to do is we're going to take a look at something called residuals. And residuals happens when we put the two together, when we put the scatter plot together with the line or curve of best fit. We've also been talking about the correlation coefficient, the R value, and the R value measures the predictability of the model. In other words, how well can this model predict into the future, or interpolate or extrapolate. Although the R value is an excellent measure, it doesn't tell us whether the model is appropriate, only whether it does a good job at predicting. So using what we call the residuals are going to help us determine if the regression equation that we chose, whether it was linear, quadratic, or exponential, was a good choice. In other words, should I have done a linear regression or should I have done an exponential? And the residual graph will tell me that. So today what we're going to do is we're going to examine residuals and residual graphs to determine if a linear model makes sense. Now, the key to residuals is understanding that the residual is the actual Y value that you're going to get from the table minus the predicted Y value, and the predicted Y value comes from the model, or the equation that we come up with. Now, if we were to look at a picture of this, I have a scatter plot here with a couple data values. Here's a data value here, here's a data value here. And then my line of best fit goes through them. The residual is the distance between the data point and the line. So the residual comes from the distance of the actual Y value, again from the table, minus the predicted value from the line of best fit. And that's going to be very, very important that you understand that. So in example 1, we're going to use the data below to write the regression equation, y equals ax plus b. Again, notice that they're telling me what kind of regression to do. They're telling me to do a linear regression. For the height of boys in inches based on their age in years. And we're going to round all values to the nearest tenth. So what I want you to do at this point is I want you to pause the video. I want you to run the regression equation, or run a linear regression for the data, and then come up with the equation rounded the values to the nearest tenth. Okay, so when I ran my linear regression, I got the equation y equals 2.3x plus 33.4. Now what we're going to do is we're going to use this model to determine our residuals. So part B says complete the table below to calculate the residuals. So here's our model, and that's where we're going to get the predicted value from, Now these heights, we have the age in x, and then we have the height, which is y, and that height or the y value are the actual values, the actual y values. So when I do my residuals, this is the value that I'm going to use with the subtraction. Now the predicted value comes from taking the x, substituting it into the model to get the predicted value. So the 44.9 is the predicted value. Now to calculate the residual, I do the actual 44.5 minus the residual 44.9, and my residual is negative 0.4. So now what I need to do is I need to complete the chart. I'm going to do one more with you, and then you can fill in the rest of the chart. I need a predicted value for when x is equal to 6. So I substitute 6 into the model for x. I throw that into my graphing calculator, and I get 49.5. Now, to get the residual, I take the actual y value, 46.9, and I subtract the predicted, which I calculated to be 49.5, and I get the residual of 0.2. So now at this point, what I want you to do is pause the video. You're going to fill in the rest of the table, both for all the predicted y values and for the residuals, showing all your work, and then we'll come back and take a look at a graph of the residual plot. Okay, now I did notice a mistake when I went back and I was looking at my table. When x had a value of 6, and I substitute a 6 into the model, I end up with 47.2. So now the actual is 46.9 minus 47.2 equals a negative 0.3. I accidentally read the next line underneath it. So your predicted values should be 47.2, 49.5, 51.8, 54.1, 56.4, 58.7, 61, and 63.3. And then your residuals are negative 0.3, 0.2, 0.4, 0.3, negative 0.7, negative 0.2, negative 0.1, and negative 0.2 again. Now what we're going to do is we're going to take a look at the graph of the residuals, and the graph of the residuals is more meaningful than anything else. So we're going to create a residual plot based on the residual scores. So what we're doing is we're graphing the x coordinate and then the residual. So for the very first x value, I have an x value of 5, and then I had a residual of negative 0.3. And then the next x value is 6, and a residual of, oh, I'm screwing this up again. So I had a residual of 5 comma negative 0.4. And then when x was 6, I had a residual of negative 0.3. And then when x is 7, I have a residual of 0.2. Now I'm not going to continue to write out the ordered pairs, you get the idea. But at 5, I got to go down to negative 0.4. At 6, I have to go down to negative 0.3. At 7, I have to go up to 0.2. And what, again, I want you to do is pause the video, and I want you to finish graphing the residuals. So from x is equal to 8 all the way up to x is equal to 13. Okay, so if you notice, I finished filling in my residual plot, and the residuals on the graph are kind of scattered all over the place. So in part D, it says, do the points appear to follow a pattern? If the points are centered around the x-axis and are random, then the points on the original scatter plot are close to the line of best fit. If the points form a curved pattern, then a linear function should not be used. So the key here to residual graphs is we don't want a pattern. We want randomness around the x-axis. So is there a pattern? There's no pattern. There is randomness around the x-axis, meaning that the linear model or the linear equation was a good fit to the data in the initial scatter plot. In other words, the line of best fit those data points very, very closely. So now we're going to take a look at some examples of some other residual graphs. In example 2, we model 2 data sets using linear models. The resulting plots are shown below. So both of these are residual plots. Okay, which residual plot, plot A and plot B are both residuals, indicates that a linear model is a good fit. And if we want a linear model to be a good fit, we want random residuals. Random residuals around the x-axis. That's the key to a residual graph. So if I look at plot A and plot B, I want the points to be scattered around the x-axis. And the only one that does that is plot A, because plot B tends to form more of a parabola picture. So plot A indicates a good linear model, because once again the points are random around the x-axis. They're evenly distributed around the x-axis. Okay, in number 3, 4 athletes on a track team are comparing their personal bests in the 100 meters and 200 meter events. They construct a table of their best times as shown below. So we've got 4 different athletes with a 100 meter time and the 200 meter time. And then what I did was a scatter plot of the results, including the least squares line. Now, least squares line is just like a linear regression. It's the same thing. So notice that the line isn't really near the ordered pairs, but it's tending to go through them at a pretty even point. A says, use your calculator to find the equation of the least squares line, which is just the line of best fit, rounding the values to the nearest thousandth. And then part B says, use your equation to find the predicted 200 meter time for the runner whose 100 meter time is 12.95, and find the residual for the athlete, rounding your answers to the nearest hundredth. So what I want you to do is I want you to pause the video, I want you to do A and B, and then we're going to end up finishing the table for part C and looking at the graph for part D. So go ahead and pause the video and see if you can do A and B, and then actually you can go down and calculate the residuals for the remaining athletes, which is part C. Okay, so I did my regression equation. I got y equals 1.511x plus 7.526. Then I used the equation, I substituted the 100 meter time of 12.95, which is my x value, into my model, and I got a predicted value for the 200 meter time, which is 27.09. Now to calculate the residual is actual minus predicted. So the actual 200 meter time for that individual was 26.68. And I got that from the table on the last page. So I did the actual minus the predicted, 27.09, and I got the residual of negative 0.41. So I substituted that into my graph. Now I calculated the rest of my residuals, and what I did was I took the x time of 13.81, I substituted it into my model, and I got a value of 29.48. And then I subtracted this is the actual time. That's the 29.48. When I substituted into the model, I got the predicted time, which is 28.39291, and I got 1.09. And I did that for all four values. Now, using the axes provided, construct a residual plot. So for athlete 1, he had 12.95 in the 100 meter time and negative 0.41. And then 13.81, he had 1.09. And then 14.66, he had negative 1.57, which is down here. And then at the 14.88, he had a residual of 0.92, so he's up here. And there's my residual plot. Now, if you notice, the residuals are random about the x-axis, meaning the linear model is a good fit. So your homework tonight is on worksheet day 13 on residuals.